professeur en physique de l'archéométrie, on peut dire ça, ou en archéométrie, tout simplement, à l'université de Bordeaux-Montaigne. C'est le directeur du laboratoire IRAMAT-CRP2A, qui est l'UMR du CNRS aussi, avec le CNRS. Donc le titre de son exposé sera Archéomatériaux, plus de 20 ans de coopération scientifique du laboratoire avec des chercheurs du Pérou. Voilà. Donc tu as, c'était combien? Une demi-heure. Voilà. Il n'y aura pas de questions, les questions seront réservées à la pause, parce que sinon on ne va pas tenir. Voilà. Merci. Je t'en prie.
Merci, chers collègues. Madame la consul, mesdames, messieurs, chers collègues, cher Rolf, merci de cette invitation. Je vais être très rapide parce qu'il ne faut pas perdre de temps, on a 30 minutes. J'ai beaucoup de diapos, je vais essayer aussi de faire très très vite. Je suis Rémy CHAPOULIE, c'est à CRI, et je suis un des profs, effectivement, à l'université Bordeaux-Montaigne, qui est plutôt une université de sciences humaines et sociales. Et curieusement, je suis dans un laboratoire qui, depuis 35 ans, fait de la physique appliquée à l'archéologie. Alors, parmi vous, de ce que j'ai pu voir dans les présentations, nous n'avons que des matériaux modernes et des méthodes particulièrement novatrices. Moi, finalement, je ne sais pas trop me décrire, si ce n'est que je fais de la physique appliquée, mais je fais aussi de la chimie analytique et de plus en plus d'archéologie, ce qui fait que certains de mes collègues me confondent pratiquement avec l'intitulé d'un archéologue. Mais regardant Jorge, je me dis, it's better to move now to switch into English so that everybody can understand. So I feel sorry for this introduction, but shortly it was necessary. Just to say a few words. The institution in which I'm working is called Institute of Research for Archéomatériaux, and the CRP2A acronym is for Centre de Recherche en Physique Appliquée à l'Archéologie. Okay, doesn't really matter. What I wanted to talk is the collaboration that we settle for more than 20 years between our laboratory and some of the universities in Peru. So actually it started for more than 20 years when some people discovering a very, very famous site called Sipan, and you probably heard about the Lord of Sipan that was discovered in 1987 by a very famous archaeologist named Walter Alba, which I met some years ago. And actually from there, it was the idea of trying to use a dating method to know more about the chronology of this site. And in our field, something very important for us physicists is to share data using different methodologies. You probably have heard about carbon-14, C14, which is ever so used, but which is far better is to use two different dating methods working on different materials to make sure they cross over and the chronology will be precise and right. That is very important. That's the way we started working with archaeologists in Peru. On the left, the slide is showing some of this excavation in which we excavated some of the ceramics that were dated using the luminescence method. Maybe you don't know exactly how it works, because I know that carbon-14 is ever well known, but maybe with luminescence you can have some ideas. Also interesting is some of the metals that have been encountered here, and because these very famous things have also given some of the works we performed on these. So it all started, as I said, in the 90s, and I just got an extract of the publication that was released by some of the people, young researchers. I made all the names here, Céline Roch or Emmanuel Bartana, and also Pierre Guibert, who used to be one of the directors of the Institute, and also Max Ferrer, who was the creator of the Institute, and with some of the colleagues, as I said, from Peru, Walter Alba, and also Daniel Levin, who used to be a professor in Paris 4 Sorbonne. And so, just to give an extract from this, the idea was, thanks to two independent methods, as I said, thermoluminescence, TEL, and C14 were implemented on materials of different natures. Now possible to place with a good degree of confidence the burial of the priest during the course of the 8th century of our era. That was a very good moment because the Lord of Sipan was probably one of the best known excavation sites in North Peru. So some of the former work that were done on the metals and on the chronology. But now I will switch directly to some very recent publication and some work that has been made by one of the assistant professors that we have at our university, That's a lady, she's called Christelle Lahaye, and from the luminescence method, she also developed, with the other colleagues that we have in our lab, the optical stimulated luminescence, called OSL. And actually, one of the biggest questions that we tried to give answers to were the first settlements on the American continent. You may have heard about these theories that would suggest that men came over from the north, coming to the coast, and maybe getting either on the east side of the South American continent or on the west side using boats. And actually the first hypothesis was saying that these men were no older than 11,000 years. But what happened to what Christelle has done, sorry, I'm mixing the two things, sometime in the Brazilian country, she went with some archaeologists from the Paris University also, and she participated in the excavation. And here, using a thermoluminescent dating and OSL, as I said, on single grains that she took over from the excavation and the sediment that were found in this thing, and measuring some radioactivity, I will explain later. Then she performed some dating things showing that the occupation was something like 22,000 years ago, which made a bit of a difference from the 11,000 years that was primarily suggested. So you see here some of the stratigraphy in which she took over some lithics that were, according to the experts, that were made, sculptured by ancient men, because lithics were used as tools, as you know, and they were prepared to make tools. And so, taking this as the expertise from this archaeologist with which she's working, then she proved by dating the sediments around that they came from areas around 22,000 years ago. Here she is working in the lab with the red light, because I will say a few words on that later. Some more sites were taken over to see whether this average data was right, and it corresponded actually with the C14 data, and actually here the average was something around 25,000 years before present. So that makes good agreement for saying that they were a previous occupation in the Southern American country. Other sites still from Brazil, and also giving other similar ages. So that was something very important, using either the thermoluminescent, the previous things that we did with the CPAL excavation, and also the optically stimulated luminescence. I will say also a few words about cathodoluminescence that could provoke using electron beam to have a look to ancient materials too, and to try to separate and discriminate some of the productions. So just to say how it works, I will not give too many equations or things like that, because that has been developed in publications. But just for those who do not know, just a few things how it works. Everything starts with the idea we work on crystals. Crystals like quartz, which is shown here, as you know, are never perfect. In physics of solid state, you all know about defects, which we call defects. There are either chemical impurities, it can be titanium, aluminium, germanium, taking the place of the silicium atom, or they can also be defects like in the formation genesis of the crystal, when they separate, and then you got vacancies, and you got clusterings and things like that. So everything makes it something available to what? To receive electrons that can be mobilized, moved, due to what? Due to natural radioactivity. Everybody knows about radioactivity. We know about uranium, thorium, and potassium. We all know that in this world, you have some potassium. Therefore, we all know that we receive some rays coming from the radioactive potassium. Of course, the amount is very low, obviously, hopefully. I would say that during the geological times, since the quartz crystal has been taken out from the volcano, for example, then it has received the irradiation from uranium, thorium, potassium, with different half-lives, times, whatever. And what happens is that in the defects, represented here like different things, like this atom, that we can summarize as being like traps into what we represent the band energy scheme, these electrons can be trapped. And the more they stay in the ground, the more radioactivity moves the electron to fill the traps. And so, when we find them in the excavation, when the quartz has been taken and it is somewhere in one of the ceramics, sorry, JX animation is not useful really. So what can happen? It's just that the potter, the craftsman, when he wants to make this ceramic here, he has to heat it up. He takes the sand, he takes the clay, mix it up, make the shape, nice, maybe some paintings around, and he has to heat it up to what? To make it solid, so that you can use the ceramic to transport water, to transport wine, to transport cereals, whatever. So it has become solid. At that time, with the heating process here, which I summarized, I don't know if I put it here, yeah. All the geological dose that has been accumulated during the ancient times, once it is heated, all the electrons will be taken away. I'm sorry. Oh, that's the heat. Sorry. That's the fire for this time. And that's very important because after this, the ceramic, what's going to happen? It will be lost somewhere in the ground and then the sediment will recover. And then 1,000 years, 2,000 years after, an archaeologist will there make the excavation. And so, during this time, actually, you see that after the heating, which has released all the electrons from the traps, then the radioactivity, as it is very common, and doing its work regularly, uranium, thorium, and potassium, with alpha particles, beta particles, gamma rays, then they produce again the filling of the traps. And that is very important for us, because this corresponds to what we call the archaeological dose. And thus, when the archaeologists take the ceramic to the lab, we look at the ceramic closely. And what are we going to do? We're going to heat it up again. And then we're going to release all the electrons. And when the electrons will be released, they will produce luminescence. We measure the luminescence. And so we reach from here the possibility to come back to the what we call archaeological dose. That is a radioactivity equivalent dose. So you see, we have this archaeological dose here, the heating in the lab. And with the luminescence, we can measure the quantity of the archaeological dose. So we have the zeroing moment, which is the moment when the firing happens with the craftsman, that is making the ceramic solid. So we measure, that's the archaeological dose running over according versus time. So we have the natural dose from here. And what are we going to do then? Because there is no more radioactivity. We have radioactive sources in our lab, so we will reintroduce radioactivity in the grains, in the quartz. But in that time, in that case, we know what we're going to introduce, because the radioactivity sources are calibrated. We know them perfectly well. So we will put a dose, let's say D1, let's say D2, let's say D3. So we can construct a linear curve, not all time, so linear, but, and then starting from here, we know these three things. We obviously can have much more, but then we can construct the curve and then go back to the natural dose. And that's it. We got one of the first element from the equation. The equation is what? Is the age, is the equivalent dose I'm talking about. But there's something missing. We need to know how much the radioactivity is doing this work for 1 year. So we have to go to the ground to measure the radioactivity. Like what? Putting sensitive dosimeters, sulfate, carbonate, things like that, alumina, and also to measure gamma rays using spectrometers, dedicated spectrometers. That is why we need to go on the field. And then we have the annual active radioactivity, and then that goes back to the age. One thing, accuracy is more or less 5%. If you work in antiquity, medieval times, in our European countries, it's not so good, because it's better to read texts, much better, much more precise. But sometimes when you have no text, it can be very interesting. And also something nice is to go much further than radiocarbon. Radiocarbon can reach, do you know, let's say 45,000, 55,000 years, no more. Because then the amount of radioactive carbon is not sufficient enough to make it possible to measure. With this luminescence method, we can reach 1,000, 300,000, sometimes 5, depending on the quartz and the amount of defects it has included. So that was the dating, that was a bit similar. Let's go back. Well, important thing is that chronologists need to be in the field, in the ground. Before, some of the archaeologists took over the material and said, oh, this is it, do what you can. This is not possible. We need to go on the field, because what? We have to collect ourselves, make a pre-selection, because they need to be heated enough. Otherwise, you will measure geological times. Well, that can be very interesting for in geosciences, of course. For something interesting is that nowadays we work on sediments with the OSL. Why? Because some of these can be bleached by the sun. I will say in the second slide. Just to carry on with the chronologist needs to be in the ground. It's a sampling. The bricks also can be dated. That can be very interesting for some of the biggest monuments that we have in the world in Peruvian country. Again, some dosimetry in situ using different dosimeters that we can produce ourselves or buy, depending on what we want to do. And again, same slides. As I said, sediments also. Why? Because they can be bleached by the sun. And in that case, it's not a heating that's going to erase the previous dose. It is the sun. And in that case, you can measure ancient radioactivity that's been stored by stones if they've been moved in buildings. So that opens the variety of dating materials, like those which are used into constructions. They were set into masonry, and then again you can reach this archaeological dose. So the research in chronology is a huge field involving methodologies that is crossed with archaeomagnetism in our lab. I will not talk too much with this today, it's too short. But our programs deal with masonry, as I said, Paleolithics in southwest of France. We also work in Africa and Near East with the appearance of modern man, and also in South America, as I've just shown previously. The equipments that we need is a lot of chemistry for sample preparation. We need to separate grains. We work mainly on quartz, can be on feldspar. We also use some radioactivity measuring systems. At the moment, we got 8 machines. Probably gives us the biggest possibility in Europe, and some detectors and dosimeters to take over in the field, and also a big amount which is developed in the Rennes University with us in Bordeaux about archaeomagnetism. So now I move to the third luminescence application that we can use, the one that you provoke using electron beam, which can be provoked in a scanning electron microscope, because this is a possibility, not so used actually, unless you want to detect some of the defects into semiconductors. But for us, the application is still with ancient material. So let's have a look to what can happen. As I said, mainly the luminescence is due to chemical impurities and some other types of defects, but mainly chemical impurities. You see in quartz, the luminescence can be orange to violet. It's quite wide, difficult to discriminate. With feldspar, can be from blue, pinky, or yellow-green. With calcium carbonates, can be orange-red. With zircon, you can have either blue. Some others, like mica, including iron, which is a poison for us in luminescence, give no luminescence. So anyway, we get images and spectroscopy. So about the physics, everything is known in luminescence nowadays. So let's go to the applications. So as I said, it doesn't need to have a bigger equipment. You can have a microscope and have images and do some image analysis. So that is the size of the sample you need to put into the little chamber that you put under a primary vacuum, and then you perform image analysis. Well, I take over for this because these are very traditional things. As I said, you can also perform the luminescence investigation using a scanning microscope. You need to have a ellipsoidal mirror that you can set somewhere in the chamber. So we dedicated one of our equipment using this kind of thing. So here this chamber, and associated with this spectrometer, which is linked to the chamber, taking over the luminescence and using this route to get the spectra in the end, like this one, for example. That's a work that's been done by one of the geologists I was working with some years ago about zircon grains. Zircon grain, chemical formula here, can show different light or less strong luminescence in the blue. But if you look to the spectra, then you can see large bands and very narrow peaks. So in the end, you can even separate the spectra, the production of the luminescence. Let's see here in the blue area, the dysprosium was responsible for the blue emission. The terbium was itself responsible for the green emission, and the gadolinium was also producing some near UV emission at 311 nanometer. So that makes a mapping of the chemical impurity that you can detect like X-ray when you perform the mapping in X-ray with a scanning microscope. But that's even more also interesting because you can detect these impurities at a very, very low level that you could not detect with the XRF. And just to give one application that we performed using, again, a zircon grain, was this kind of thing on the Colossus Amendment somewhere in the middle of Egypt, where we took some sample of sandstone. This is one of the sample. Petrography says, okay, that's mainly quartz with a cement of quartz, and scanning microscope showing some inclusions of iron, and luminescence showing the luminescence of quartz from orange to violet. And in between, you could detect one very little grain that was ever so easy to detect because of the blue emission, and the interpretation was a zircon grain. Then we could reach the origin of the stone coming from the Koreas from the north of the Egyptian country. So that's good for detecting the provenance of some stones or even some ceramics. What about ceramics, as I'm saying? Ceramics, let's say these two from the Neolithic Sudan. And you see, in luminescence, very easy pictures, blue dominating, violet dominating, different things. So the archaeologists are very fond of this. And that is why we started some long time ago, some connection with the archaeologists and students that we exchanged. And we had some experiments either with metal, pigments, and ceramics. So rapidly, some here showing some of the metals that have been encountered as in the Mochica period, about the protectors that the warriors had beneath, you see. And here, using meteorography and scanning microscopy, we can demonstrate the regular copper leaf that was made with a very polished surface on which gold and silver sat on the surface with a very low amount at 10 microns depth, which said that the techniques used was a fusion gilding. About pigments, some of the ancient students that we had performed some very good study of the polychromy of the mural paintings from the Huaca de la Luna and Trujillo, Peru. She's there in the field using the X-ray portable system that was held by one of my colleagues I will talk about. And so she wanted to try to get interpretation for conservation objectives. What are the pigments? How can they protect them? It's not easy job at the moment. I still have a lot of problems. And also she was looking for the raw material provenance. You see here from this map that the red pigment mine was identified not too far in Tambo, Colorado, somewhere in the south. About ceramic, mainly my job was done with this professor that is at the PUCP, Luis Rémy Castillo, who used to be, by the way, very recently Ministry of Culture, as I heard. for some months, short period. It's true.
Not the biological time.
As you said previously, it goes like that.
It's
Okay.
not geological time.
Maybe not. Very modern time. And this other student that we had some time ago in a master degree and a PhD is called Nino Del Solar, the lab there, is now a researcher at the Ministry of Culture in Cusco, and I guess you know him. So what did he perform? He went into the study of Mochica ceramics. Some of the examples are shown here. That comes in the Jequetepeque Valley in the north of the country. And the question was trying to understand about the melting pot in these cultures. I mean, what about the acculturation processes in the 8th, 9th, and 10th century AD? So actually the question was, how were they influenced those potters from the coast, this is the ocean, and from the highlands in Cajamarca, another big city somewhere producing some of the ceramics. So the idea was to compare the chemical composition, the structures, and maybe some differences into the decoration things. So I'm not going to do the thesis again, because it has done, in less than 5 minutes, not possible, but just believe me, it works. So he separated the things, and that was a hell of a job. And everything has been set into a book that we published recently, last year actually, that is published somewhere in the French Institute of the Andean Studies, IFEA. Archéomatériaux, it's called, with all of these guys around. It's all in Spanish, and that was my wish, to send a book only written in Spanish, because there are so many in English. I mean, why not in Spanish? So this one is. I'm quite happy. So again, with Nino's work, that was tremendous about scanning microscopy, EDX, and XRF. He demonstrated that it's no use to use these big machines. With a portable system, he could do the same. And here for the engobes, the things that cover the ceramics, made a demonstration of trying to know about the chemical composition and about the decorations also. He made an interesting discovery. He showed that the presence of manganese that was obtained with XRF and Raman spectroscopy, but the presence of manganese showed some influence on the Wari civilization, which was a bit southern in the actual Bolivia, coming to influence those traditions in the north of the present Peruvian country. Okay, now we started very recently a new thesis with this young Peruvian gentleman, Dante Pareja Ñosa, in collaboration with the University of San Marcos, Luisa Diaz, and some colleague from the University of Brussels, and also Javier Iñáñez from the University of the Basque Country in Spain, working on trying to know more about the civilization. It's called Ixma, close to Lima in Pachacamac. So now I'm nearly finished. So now just a few things about what we can do. What else can we do in our lab? Exploring with hyperspectral system. That's ever so performing, because this is non-destructive at all. And we use either benchtop systems and portable systems. This is a very teeny one, no bigger than a camera that you have in your pocket. A bit better, a bit bigger. Sorry. And what do we want to do with this? Trying to separate again, go further with the absorbance spectra. And if you have a look to the hyperspectral imaging, I'm going to say it rightly. You see here the two red dots. They look red, okay. If you look into the infrared full color, then one is looking orange, the other one is looking yellow-green or something. Makes it different. And if you separate them, then you will define that decoration is not done with the same material. This is a gold metal, okay, number 2 here, there. While number 1 here is a pink color, which is obtained with a silicate of calcium and tin doped with chromium impurity. Exploring again, we're going into the use of terahertz to try to understand, to see if we can have a look inside without touching anything. This is an on progress thing that we want to compare with the X-rays analysis that is done under micro-computerized tomography that is using X-rays. So you see here it's quite interesting to detect cracks and vacancies and holes and the shape the ceramic was done and how it was done. And very recently, because somebody is a specialist of the LIPS systems around, and some of the colleagues from Trujillo also, we have some work done on teeth coming from a very modern collection. And just to show you some of the mapping that we got with the LIB system, I'm not a specialist on, but my friend Bruno Bousquet, working in laboratory in Bordeaux also, is showing that mapping some strontium can have a very good looking to detect what they call the neonatal line, when the baby is taken to life, and also some information about when he gets some solid food, or when he has some breastfeeding exclusively, and things like that. And if you detect barium, then you can have, happens the artificial milk, etc. So they're making links with anthropologists. I guess I'm over, and I will stop nearly down. With the LIB system, maybe we'll have a talk with it. I can use it to go into prehistorical cave to look around at the alteration that you can see here in white, which is bothering the archaeologists and the prehistorians working in the Vézère Valley, the UNESCO site where the Lascaux cave is located. And some other things with the hyperspectral thing. And to finish with, maybe this little object that we performed, that is a pattern that we developed in our lab. This is a very tiny box. Using this, you can have, with a light-emitting diode system, then you get spectropolarimetry that we can perform to get some spectra with a data bank that we are creating. And this is the research we develop in our field, using all these kind of things and many applications in physics and chemical analytics. Thank you.
Thank you.